Welcome all to the online lecture series on applied electromagnetic theory. This lecture will delve with the topics from Module 3. So this lecture is all about power, density and polarization of electromagnetic wave. Myself, Rinju Mariam Raleigh, Assistant Professor, Department of ECE, Rajagiri School of Engineering and Technology. In order to find the power flow associated with an electromagnetic wave, it is necessary to develop a power theorem for the electromagnetic field known as Poynting theorem. And that's our subject of interest for this particular lecture. So in this lecture, we will learn about power density of electromagnetic wave and Poynting vector theorem. And in order to understand today's lecture, you need the basics from vector calculus. You should be thorough with Maxwell's equations and electromagnetic wave propagation in different media. So let's take a quick recap of what we learned in the previous lectures. In second module, we learned wave is a function of space and time. And when we talk about wave propagation, there is propagation constant represented by gamma and its value is equal to alpha plus j beta, where alpha represents attenuation constant and it's a measure of spatial decay of the wave in the media. Beta represents phase constant and it's a measure of phase shift per length. Wavelength is represented by lambda and it is related to phase constant as lambda is equal to 2 pi by beta. Eta represents intrinsic impedance, that's equal to E by H, where E represents electric field intensity and H represents magnetic field intensity. The intrinsic impedance in free space is given by eta naught and that's equal to root of mu 0 by epsilon 0, that's equal to 120 pi or 377 ohms. So we need all these basics in order to understand the Poynting vector, the power density associated with the electromagnetic wave. Every electromagnetic wave has got an electric field and magnetic field associated with it. Now let's see what is a transverse electromagnetic wave or TEM wave. It is a wave in which both electric and magnetic field are everywhere normal to the direction of wave propagation. Or in other words, we can say an electromagnetic wave that has no electric or magnetic field component along the direction of wave propagation is called a transverse electromagnetic wave. Now what is polarization? That is the direction in which the electric field points. That's called polarization. And that will be our next subject of interest. When the wave travels through different media, suppose if the medium is free space or lossless dielectric, the expression for electric field intensity and magnetic field intensity is given as this. Here, E0 represents the magnitude of electric field intensity and the wave is propagating along positive z direction and electric field is pointed along x direction whereas the magnetic field is pointed along y direction. So this expression is plotted here. It is short here. Here the electric field it is along x direction and magnetic field is along y direction. So this particular plot is an example for a TEM electromagnetic wave because in the direction of wave propagation there is the electric field and magnetic field, they are not pointing. Electric field is along x direction whereas magnetic field is along y direction. Power density of electromagnetic wave. The energy can be transported from one point to another point by means of electromagnetic waves because electromagnetic waves are propagating through the medium. And the power flow associated with an electromagnetic wave can be obtained from Maxwell's equation, or precisely they can be obtained from Maxwell's curl equations. So what is power density? Power density means that is power per unit area. So in order to compute the power density associated with an electromagnetic wave, let's consider the Maxwell's curl equations. That is del cross E is equal to minus dou B by dou T. So that I have written here it as minus mu dou H by dou T. Another Maxwell curl equation is del cross H is equal to J plus dou D by dou T. That is equal to del cross H is equal to sigma E plus epsilon dou E by dou T. So we'll focus on deriving the power density of an electromagnetic wave. So here let's start taking the dot product of the equations that we have obtained now. So first let's take the dot product with E on both sides of equation number 2. So equation number 2 is del cross H is equal to sigma E plus epsilon dou E by dou T. So let's take dot product with E. That's equal to E dot del cross H is equal to sigma E square plus E dot epsilon dou E by dou T. So that's equal to sigma E square plus E dot dou E by dou T is equal to 1 by 2 dou E square by dou T. So we will get E dot del cross H is equal to sigma E square plus 1 by 2 epsilon dou E square by dou T. Next, let's take dot product with H on both sides of equation number 1. So equation number 1 is del cross E is equal to minus mu dou H by dou T. So let's take dot product with H on both sides. That is H dot del cross E is equal to minus mu H dot dou H by dou T. Now H dot dou H by dou T, what it is? It is half dou H square by dou T. So you will get it like minus mu by 2 dou H square by dou T. So let's number this as equation number 3. And taking the dot product with H on the equation number 1, let's number it as equation number 4. Suppose if A and B are two vectors, then del dot A cross B is equal to B dot del cross A minus A dot del cross B. So let's say A is vector E and B is the magnetic field vector. Then del dot A cross B is same as del dot E cross H, because we are assuming E is vector A and H is vector B. That's equal to H dot del cross, that is H dot del cross E minus E dot del cross H. So that we have, let's number it as equation number 5. So what's our aim? We want to compute the power density associated with an electromagnetic wave. So this is the basics that we have applied in solving this equation, that is E dot dou E by dou T. That is E dot E is E square, dou E square by dou T is 2 E dot dou E by dou T. So from here we have taken half dou E square by dou T. Right now we have got 3 equations. We have got equation number 3 with us, 4 and 5. So let's substitute equation number 3 and 4 in equation number 5. Equation number 5 is del dot E cross H is equal to H dot del cross E minus E dot del cross H. So let's write del dot E cross H is equal to, what is H dot del cross E? That is minus mu by 2 dou H square by dou T. What is E dot del cross H? That's from equation number 3, that is sigma E square plus half epsilon dou E square by dou T. So that I have substituted for H dot del cross E and E dot del cross H, and you will get this expression as del dot E cross H is equal to minus sigma E square minus dou by dou T plus dou by dou T of half epsilon E square plus half mu square. So now let's take integration over the volume on both sides of this particular equation, that is over del dot E cross H. So we will get it like volume integral del dot E cross H is equal to minus of dou by dou T volume integral half epsilon E square plus half mu square minus volume integral sigma E square dV. So here we have all our integrals on, all the integrals are taken over volume, and we are talking about power density. Power density is associated with power per unit area. So in order to make it an integration over area, let's apply divergence theorem to the left hand side. So applying divergence theorem, that is over volume del dot E cross H, we will get surface integral E cross H dot ds. So that will be equal to minus of dou by dou t volume integral half epsilon e square plus half mu h square minus of volume integral sigma e square dv. Here, surface integral E cross H dot ds is equal to minus dou by dou t volume integral half epsilon E square plus half mu square dv minus volume integral sigma E square dv. This expression is called Poynting theorem. Here, E cross H represents the total power leaving a volume, and these terms, the first term on the right hand side, this represents the rate of decrease of energy associated with electric field and magnetic field. Since here it is minus dou by dou t, we are calling it as rate of decrease. And half epsilon e square and half mu s square, that represent the energy stored in electric field and magnetic field. Whereas the second term on this right hand side, that is integral sigma e square dv, that represent the ohmic power dissipated. Here E cross H, that is electric field vector cross magnetic field vector, that vector is called Poynting vector represented by P. So P is equal to E cross H, and that represents the power density, that is, so its unit is watts per meter square. And Poynting vector, it represents the instantaneous power density associated with electromagnetic field at a given point. So this is one important point that you have to keep in mind. Poynting vector P is equal to E cross H, and this will give you power per unit area. So how can you find out the total power? So that is by integrating the Poynting vector over the closed surface will give us the net power flowing out of that surface. So we can write total power P dot is equal to surface integral P dot ds, where P represents the Poynting vector and its value is equal to E cross H. The unit of total power, it is measured in watts. So here I already mentioned E cross H. This first term, that is the term on the left hand side, that represents the total power leaving the volume, and the first term on the right hand side represents the rate of decrease of energy stored in electric field and magnetic field, and sigma e square term, it is associated with the ohmic power dissipated. So the Poynting theorem states that the net power flowing out of a given volume, that is the net power flowing out of a given volume, is equal to the time rate of decrease of energy stored within the electric field and magnetic field minus the ohmic losses. So that is what I've showed here pictorially. So here there is some input power. So out of the input power, some is stored in electric field and some energy is stored in the magnetic field, and some is getting dissipated as ohmic losses, and rest of the power will be flowing out of the volume. Here P, the expression for P was P is equal to E cross H. So that means P is normal to electric field and magnetic field. Or we can say the direction of Poynting vector is along the direction of wave propagation represented by AK, unit vector AK. That's for a uniform plane waves. So AK is equal to AE cross AH, where A cap E represents the direction of electric field and A cap H represents the direction of magnetic field, and A cap K represents the direction of wave propagation. So keep in mind the direction of Poynting vector or the direction of power flow is same as the direction of wave propagation. So the Poynting vector, it will point along the direction of wave propagation, and this causes vector P to be regarded as Poynting vector. Okay, it points along the direction of wave propagation, and that is how it has got that name. So now let's consider a wave propagating along z axis, and electric field along x-axis and magnetic field along y-axis. So from the basics of electromagnetic wave propagation in different media, we know electric field vector is mathematically represented as E0 is equal to e raised to minus alpha z cos omega t minus beta z ax cap, and magnetic field is given by H z comma t is equal to E0 by eta e raised to minus alpha z cos omega t minus beta z minus theta eta ay cap. Here alpha is attenuation constant, beta is a phase constant, eta is intrinsic impedance, and theta eta is the angle of intrinsic impedance. Now, what is Poynting vector? Poynting vector P is equal to E cross H. So let's compute the cross product between this electric field and magnetic field expression. So that we will get it like E0 square by eta e raised to minus 2 alpha z, because here we have e raised to alpha z multiplied by e raised to minus alpha z. So that will be e raised to minus 2 alpha z. Then cos omega t minus beta z into cos omega t minus beta z minus theta eta. And what about the direction? We are taking the curve, that is ax cross ay cap. Okay, ax cap cross ay cap, that is going to be az cap. This ax cross ay cap, that we understood it as az cross from the basics of vector calculus. So we can write the Poynting vector pz comma t is equal to E0 square by 2 eta e raised to minus alpha z cos 2 omega t minus 2 beta z minus theta eta plus cos theta eta az cap. How I got this expression? This cos omega t minus beta z and cos omega t minus beta z theta eta, it is in the form of cos A cos B. So cos A cos B is same as 1 by 2 cos A plus B plus cos A minus B. So that is the function that I have applied here, the trigonometric function I have applied here. So this is the expression for the Poynting vector, and from this particular expression we know what is Poynting vector. It represents a power density, so it is measured in watts per meter square, and keep in mind it is dependent on time, because the expression that we have got right now, it is a function of time. It is cos omega t. Then so omega t is there, that means it is dependent on time, and the power factor that we have obtained here, it is a time varying factor. Okay, the power is, it will vary with respect to time. So next let's find time average of Poynting vector. Right now what we got was Poynting vector. So next let's find time average of the Poynting vector. So let's take P average, that is equal to 1 by t integral 0 to t p dt, where P vector is our Poynting vector. So let's take, okay, so first let's substitute for the Poynting vector. Okay, the expression that we have got right now, that is E0 square by 2 eta e raised to minus 2 alpha z cos 2 omega t minus 2 beta z minus theta eta plus cos theta eta az cap dt. Now let's take the integration inside the brackets. So we'll get it like E0 square by 2 eta e raised to minus 2 alpha z az cap 1 by t integral 0 to t, the first term, that is cos 2 omega t minus 2 beta z minus theta eta dt plus 1 by t integral 0 to t cos theta eta dt. So this we have to compute right now. So what is 1 by t integral 0 to t cos 2 omega t minus 2 beta z minus theta eta? So that answer will be 0, because the cos wave, it is a periodic time varying signal, and when you try to find the average value, that will be 0. So integral 0 to t 1 by t integral 0 to t cos 2 omega t minus 2 beta z theta eta, its integral value is actually 0. Second term we have is 1 by t integral 0 to t cos theta eta dt. So that let's find out what it is. It is 1 by t integral 0 to t cos theta eta dt, that is going to be 1 by t into cos theta eta into t. So that will be same as cos theta eta. So let's substitute that. So our answer will be E0 square by 2 eta e raised to minus 2 alpha z. Then first term integral, that was 0. What is the integral of the second term? That is simply cos theta eta. So that I have substituted here. It is cos theta eta, and it is power is pointing along which direction? Okay, it is along the direction of wave propagation, and that is Az cap. So this average, that is a time average of Poynting vector, that's also represent the power transmitted per unit area. But look here, this expression, there is no variable t. That means this particular, the time average that we have got right now, that is the time average of Poynting vector p average, it is time invariant. It is time invariant. But this is also has got a direction, that means it is a vector, but it is time invariant, and it is measured in watts per meter square. So if you take the integration over a given surface of this average vector, you will get the total power. That is the total time average power crossing a given surface given by P dot is equal to surface integral P average dot ds. Because P average, it also gives the power per unit area. So when you take the integration over the given surface, it will give you the total time average power. So keep in mind this unit of total power, that is watts, and that will be a scalar quantity. So now we have learned some theory, okay? How much is the power carried by the electromagnetic wave? We learned Poynting theorem, we learned Poynting vector, that is actually power per unit area. Then we learned time average power and how to compute the total power. So now let's work out one problem. Okay, it is given in a non-magnetic medium, E is equal to 4 sine 2 pi 10 raised to 70 minus 0.8x Az cap volt per meter. Find epsilon r, that is relative permittivity, eta, that is intrinsic impedance of the medium. Second part is time average power carried by the wave, time average power, so that is a P average. And third part is total power crossing 100 centimeter square area in the plane, on the plane 2x plus y is equal to 5. So let's see how to proceed this problem. In the question, what is given to us is electric field, that is E is equal to 4 sine 2 pi into 10 raised to 70 minus 0.8x Az cap volt per meter. So let's compare it with our standard form. It is E0 e raised to minus alpha x sin omega t minus beta x Az cap volt per meter. So comparing with the standard form, we can understand e raised to minus alpha x is actually 1. What does it mean? Alpha is equal to 0. That means attenuation constant is 0. So if alpha is equal to 0, our medium can be a free space medium or it can be a lossless dielectric medium. Since beta is not equal to omega by c, it means the medium is lossless dielectric. So now let's start finding out epsilon r and eta. So in the question, what we have only the expression of electric field, and for a lossless dielectric medium, we know beta is equal to omega root mu epsilon. And this is a lossless dielectric medium, so mu is actually mu 0 mu r and epsilon is actually epsilon 0 epsilon r. But here it is clearly given it is a non-magnetic medium. That means mu r is equal to 1. So we have beta is equal to omega root of mu 0 epsilon r. Now, what is beta? Just comparing with the standard expression, we will get beta is actually 0.8. It is sine omega t minus beta x. So here it is minus 0.x. That means beta is equal to 0.8. So here we know what is beta. Beta is 0.8. That is known to us. Omega value, it is 2 pi into 10 raised to 7. That is also known to us. Mu 0, epsilon 0 value we know. So the only unknown here it is epsilon r. So let's try to find epsilon r from phase constant beta. So we will get root of epsilon r is equal to 0.8, that is a beta, divided by omega, that is 2 pi into 10 raised to 7, root of mu 0 epsilon 0, that is mu 0 is 4 pi into 10 raised to 7 and epsilon 0 is 8.854 into 10 raised to minus 12. So substituting, you will get it as 12 by pi, and 12 by pi is actually root epsilon r. Then what is epsilon r? That is the square of 12 by pi, and that's going to be 14.59. So we just found out the relative permittivity. So what is our next task? We want to find intrinsic impedance. So what is intrinsic impedance expression? Eta is equal to root of mu by epsilon, and we know our medium is a lossless dielectric medium. So mu is actually mu 0 mu r and epsilon is epsilon 0 epsilon r. And since in the problem it is clearly stated that the medium is a non-magnetic medium, mu r is equal to 1. So we get eta is equal to root of mu 0 divided by epsilon 0 epsilon r. Now root of mu 0 by epsilon 0, what it is? That is the intrinsic impedance in free space. So let's substitute as 120 pi, then root epsilon r. So we know what is root epsilon r. Yes, we just found it is 12 by pi. So substituting root of mu 0 by epsilon 0 as 120 pi and root epsilon r from what we have just founded before, we will get eta is equal to 10 pi square, or it is equal to 98.7 ohms. So the second part is computing the time average power. So we know the expression of time average power as E0 square by 2 eta e raised to minus alpha z cos theta eta a cap k, where alpha is the attenuation constant that we already understood. It is 0 for our case, for the question given. And since the medium is lossless dielectric medium, it means theta eta is equal to 0. That is, the angle of intrinsic impedance is 0. This is the question given. That is, E is equal to 4 sine 2 pi into 10 raised to 70 minus 0.8x Az cap. So this was the expression of electric field vector that was given to us. So here we already understood alpha was 0 and theta alpha was 0. That means it is a lossless dielectric medium and theta eta is equal to 0. Now what is this a cap k? A cap k represents the direction of wave propagation. So here from this electric field vector we can understand the wave is propagating along x direction. That means direction of propagation is ak, that is equal to ax. So substituting alpha is equal to 0, theta eta is equal to 0 and a cap k as ax cap, the time average power will get simplified as P average is equal to E0 square by 2 eta x cap. So what is E0 from the question given? It is 4. So E0 square is same as 4 square divided by 2 into magnitude of eta. So just from the first part of this particular question we understood magnitude of eta is 10 pi square, that we have substituted here, and when you solve it you will get it as 81 milliwatt per meter square, and the power is flowing along x direction. But we have got one more part pending. We want to find the total power crossing the surface, and area was given, that is 100 centimeter square on the plane 2x plus y is equal to 5. So how to find total power if we know the time average power? So it is total power is equal to surface integral average power dot ds. So here P average dot ds is same as S into An, where S is the area of the surface and An cap represent the unit normal that is perpendicular to the surface. So what is the surface here? It is a plane 2x plus 5, 2x plus y is equal to 5. So we want to find the unit vector that is normal to that particular surface. So from the basics of vector calculus, we know unit vector for that is perpendicular to this particular surface An is equal to 2ax plus ay cap divided by root 5. So we can substitute that in our expression, that is total power P dot is equal to P average. What is a P average? That is 81 milliwatts. So it is 81 into 10 raised to minus 3 X dot, then S represents the surface area. In the question it was given 100 centimeters square. So in terms of meter, that is going to be 100 into 10 raised to minus 4. And An is the unit vector, that is 2ax cap plus ay by root 5. So solving this, you will get it like, so here we have the dot product, okay. So here you have ax dot ax, that is one term, and ax dot ay, that is going to be second term. But from the basics of vector calculus we know ax dot ax is 1, whereas ax dot ay is 0. So applying that basics here, you can solve it and you will get the answer as 162 into 10 raised to minus 5 by root 5, and that is going to be 724.5 microwatts. So this is the total power that flows through an area 100 centimeters square, that is 724.5 microwatts. So this lecture we learned about power density associated with an electromagnetic wave, Poynting theorem, Poynting vector, time average power, and total power. So, thank you, and I have referred the textbook Electromagnetics by Matthew N. Sadiku and Engineering Electromagnetics by W. H. Heath. Thank you.